So to use Civil NX and Grasshopper together, we created GH plugin in Grasshopper side. You know, like traditional structural analysis software requires a lot of effort, even for simple modifications. However, with Civil NX and Grasshopper, engineers can easily adjust models at any time and quickly generate similar models for future projects. We have some great advantages. MIDAS IT, we fully support Grasshopper integration. So first, you can use all Civil NX features. You know, we are in the second phase of development, and by mid of this year, almost all features in Civil NX will be available. And second, we are continuously improving. We are actively gather user feedback and refine the feature, so you don't have to worry about this performance. And finally, it is super flexible. It is easily import and export Civil NX models and apply parametric modeling, whatever you want. To use API, you have to understand the exact data structure for the model. As you can see here in the middle, you have to understand all these kind of logics, how each functions consist of. However, MIDAS GH simplifies this process with easy components. For example, to create a simple beam structure, you can just connect a line in Grasshopper to MIDAS GH's components, and it automatically creates elements and nodes in Civil NX. So it automatically created this information. You know, many design companies nowadays have already started preparing for design automation. You know, their implementation levels are all different, but many companies are considering this workflow to integrate both structural analysis model and BIM model. As you can see here, with a single Grasshopper template, users can create and manage both Civil NX and BIM models. During the design review process, there are frequent modification and updates. And by reflecting these updates in the Grasshopper design template, users can update both Civil NX and BIM model in real time. Finally, BIM model can be used to extract the drawings and generate the final submission documents. First, I will share how to easily create tendon profiles for PSC bridges using Civil NX and Grasshopper. So now let's go over the process of applying tendons to the structure. So tendons are defined using relative coordinates from drawings. And in this step, make sure to select the element option. The tendon profile information can be extracted as DXF format using export to DXF function in MIDAS Civil NX. As shown in the drawing on the right, you can see both XY plane, XY plane. The 2D information can be converted into 3D coordinates using an Excel-like template. Now you can have absolute coordinates for the tendons, and you can choose between the straight and curve option. Then my question is, why we need to select straight or curve option, which use absolute coordinates? Let's look at the reasons. Let's break down the differences between straight and curve and element options. The element option uses relative coordinates, making it easy to apply from the drawing, 2D drawing, right? It is very simple, but not recommended in some cases. So let's see two examples. In the first example, a tendon is applied to a straight member, and we compare the member forces for the straight and element options. As you can see on the right, for straight elements, both options give the same result, same result. So for a straight element, it might be okay to apply element option, which is relative coordinates. In the second example, a tendon is added to a curved element. The straight and curve option give similar results, but element option is quite different. As you can see here, straight and curve are similar, but element option has higher member force, right? So what causes this difference? So we have to understand the tendon loss. You know, over time, pre-stressing force gradually decreased due to the tendon loss. And there are some key reasons for this. First, anchorage slip. When tensioning the tendon, the wedges press into the anchorage, causing a slight reduction in pre-stressing force. And next one is ubu friction. Since ducts are not perfectly straight, small misalignments at support points create friction. And the longer the duct, the greater the effect. Finally, this is the biggest issue. This is the curvature friction. This happens along curved section of the duct. The sharper the bend, the more tendon loss we can check from here. First, let's compare the result of anchorage slip. Looking at the red marked area in the table, the straight and curve option show no difference, but element option has a slight variation. The same applies to the ubu friction. The element option shows slight differences compared to the straight and curve option. This curvature friction is the biggest problem, as I told you. When using the element option, as you can see here, all the value is 0. So it means like the tendon loss is not considered at all. So to ensure the accuracy, it is better to use straight or curve option instead of element option. But it is very difficult to apply the absolute coordinates of the tendon directly. So I will show you how we can overcome these difficulties we have. So what if we use Civil NX and Grasshopper together to overcome this situation? So I'd like to share how to create tendon coordinates using Grasshopper. So in this session, we bring 2D drawings into Grasshopper. The 2D drawings contains tendon shapes in different views, such as elevation view and top view. So first, we assign the desired tendon to different layers and import the layered drawing into Grasshopper. So you can bring the drawing like this, and you can activate the desired layer. So from the top view, we define the bridge center line, and from the elevation view, we set the top position of the deck. So we can set up the center line from the top view, and we can set up the top position of the deck from the elevation view. This allows us to place the tendons in 3D space based on the bridge center line. Since tendons are curved, we find the key bending points and adjust their coordinates to align with the reference line. Next, we determine the tendon position using the plan and elevation view. Then we create the perpendicular vectors along the reference line to calculate the tendon coordinates. So the XY coordinates come from the plan view, and Z coordinates is taken from the elevation view, combining them to create the final tendon coordinates. So from Rhino side, you can see the finer tendon coordinates. And finally, we connect these points to create the tendon's shape. And Civil NX modeling data can be also imported into Grasshopper as well. The GH plugin includes a component called getObject, which allows users to bring node and element information into Grasshopper. So by using this getObject component, as shown in the video, you can check all the node information and in the model, and also review the elements. And we also activate element part. You can see from the top left view, there was only nodes, but now elements are created. Now in Grasshopper side, we need to visualize 3D shape of the structure. And like as you can see from the Civil NX model, it is tapered beam section. So we should bring section information and create 3D shape as like in Grasshopper side. So we can bring the section information, and after that we can create the 3D shape for the gutter. So like this, we can create the 3D shape for the gutter. So we can also create the 3D shape for the pier as well. So after importing 3D tendon shape, the problem is how to create tendon profile on the structural model. To place tendons in Civil NX, we need two key pieces of information. First one is the tendon coordinate data, which determines the tendon path. And second one is element numbers, which define where the tendons are placed within the structure. So we already have 3D tendon shapes. However, at this stage, we don't know the exact location of the tendon or which element it belongs to. So we require tendon coordinates and element numbers. The first step is to organize the imported tendon data in sequence. During construction stage, tendons should be placed and jacked in a specific order. Therefore, tendons in the same construction stage should be grouped and managed together. To achieve this, we arrange the tendons based on their starting points by calculating the distance value. Next, we need to align the tendons with the reference line. In some cases, bridges follow the curve. This is the curved bridges. But sometimes our tendon drawing is drawn as a 2D, just 2D drawing, the straight line. So to ensure the accuracy, the tendon coordinates need to be adjusted to match the reference line and align with the actual model. The coordinates on the reference line are also applied to the modeling reference line. Then the tendons are adjusted by the required distance to finalize their placement. And after that, the tendon coordinates are connected to create a 3D shape. So the next step is to find the element numbers for each tendon. In Civil NX, elements are assigned by ID, so recognized based on the ID number, while in Rhino and Grasshopper, they are based on coordinates, so we need to match them correctly. By comparing tendon and modeling coordinates, we can accurately assign tendons to the right elements, ensuring precise placement. Now the tendon has been recognized in the model, and detailed information need to be added. So after creating tendon shape, various properties such as dock diameter, friction factor, and anchorage slip must be defined. Since there are many tendons, we already have many tendons, each one needs a unique name. First, we extract the total number of tendons to generate names automatically. So we can check the name of the tendon from here. So now the tendon is fully applied to the model with its assigned names. So you can check the tendon is applied on your structures.